Hello, welcome again to Math 1510. This is our third lecture on rational expressions. So when you see rational expressions, think fractions. So here's a generic fraction. We call the top number the numerator, and the bottom we call the denominator. We'll be using those terms a lot, so get used to it. So the first property I want to talk about, we're going to discuss a few properties. First one is called reduction. So it tells us that if we have a fraction like this, where you have this common factor, this same factor k living in the numerator and denominator, that they cancel, they divide out, and you're left with just a over b. This also goes the other way. By the way, we could start with something simpler and pick up some extra stuff. We'll see why that's useful a little later. So some examples. Start off with just numbers, and then we'll make it a little more complex. So 4 over 2. Well, the thing is, 4 can be rewritten as 2 times 2. While I'm at it, I could also rewrite 2 as 2 times 1. 2's cancel. And once we get to this step, the times 1's really not necessary. Or that denominator of 1, I should say. So that's just 2. Well, let's take this one. Throwing in a variable now. All right, well, I can make life a little easier for myself by factoring. You'll see that's going to be a common theme today. So I can do a little factoring in this numerator. We have some common factors in each term. Right, notice that both terms have at least one y in them, so I can factor out a y. But notice that there's a times 3 hidden in both terms as well. Right, 12 is 3 times 4. So I'm going to factor out a 3 and a y, so a 3y. That leaves me with y plus 4. Once I've divided both terms by 3y in that numerator, well, now we have a little canceling here. Well, maybe I'm getting a little ahead of myself. We can rewrite 9 as 3 times 3 and cancel off one of those 3's. And look at that, y as well cancels. So don't forget about that 3 that still remains there. And that's all the reduction we can do. Now we can make this even more complicated. A trinomial divided by another trinomial. So this doesn't look very reducible to me, because we expect to see, products, right? Some number times another, or some polynomial times another. We don't really see that here. We see terms. We're adding and subtracting. So it's not immediately clear how this reduces, but it does. You just have to factor first. We're going to do that for both the numerator and denominator. So first order of business, we see that in this numerator here, they each have a common factor of x. So if I factor out x, then what was x cubed is just left as x squared. Okay, then we have plus x minus 6. And this denominator, I think I just want to go ahead and factor like a standard trinomial. So there is no common factor that can be taken out of each term. This means that right away, we just factor as a standard trinomial, like we talked about last time. So I need these missing numbers to multiply to -10, and they have to add to 3. Okay, you get this simpler construction when your leading coefficient is 1. So this is the nice case. All right, so probably some 5-2 combo, right? That'll get me something multiplying to -10 and adding to 3. So is this correct? Well, if I take that inner part of the FOIL and the outer and add them together, I actually get a -3x. So that means I chose the wrong signs here. And now this will work. This will get us a +3x. So now this polynomial here, we're going to give the same treatment. And let me copy this. All right, so these missing numbers, they need to multiply to -6 and add to 1. Okay, and that'll be, I want to write the -2 there. I chose to write them in this order for the clear reason that, hey, we have these common factors in both the numerator and denominator, this common x -2. And well, that's it. That's all the commonality we have. So this is the most we can reduce. Now I want to talk about our next property. So there we talked about reduction. Now this property, we're going to discuss what do you do if I have a fraction divided by a fraction, or a rational expression divided by a rational expression. Well, the trick is don't panic, but turn it into a multiplication problem. So fraction divided by fraction, you can reframe it as multiplication. So times the reciprocal of that fraction in the denominator. Okay, so I would recommend always doing this when you see fraction divided by fraction. It's just a much easier way to go about this. So we'll do one example with this. X squared minus 4 over x squared minus 2x divided by x squared plus 3x minus 2. Excuse me, I want to do plus 2 over x. So like I just said, I have a fraction divided by fraction. I want to reframe that as multiplication just to make everything a little easier. So times the reciprocal of this. So remember, reciprocal is where you flip the numerator and denominator. Okay, and now we're ready to start taking a crack at this problem. We want to see if any reduction can be done. So I want to factor whatever polynomials I can. X squared minus 4, that's a pretty well-known one. Okay, notice here, I've got this common factor in each term, x. So if I just factor out an x, then I have x minus 2 left on the other side. So right off the bat, and I think I want to use some colors. So right off the bat, there's some reducing that we can do. Right back to normal. Well, x, that's already pretty simplified. And now the denominator, this is a standard trinomial that we can factor. So numbers that multiply to 2 and add to 3, well, a good choice is plus 2 and plus 1. And let's use blue because, there we go. It's lagging a little bit. We have these common factors here, and it doesn't matter if one is in one of the fractions and one is in the other, because when you're multiplying fractions like this, it all just mushes together into one in a very nice way. And look at that, there's one more thing. X. So we just have one thing left. Everything over here got canceled, but we still have this x plus 1, and of course that's in the denominator. So if everything cancels on one side of the fraction, then it's a 1 left. Think of it as there was a times 1 hidden there. And this is the simplest it gets. Now the last property I want to talk about. This may seem a little unusual, but adding fractions is actually harder than multiplying or even dividing them. So we're going to end there with this property, followed by an example. Just adding two run-of-the-mill fractions. So a little note here is that to add fractions, you need to have the same denominator. Or here's the more common phrasing. Pun not really intended. You need a common denominator. So with what I wrote over here, I really don't have that as of yet. B and D, I don't know if they're the same thing. Now remember when I said earlier that we can take this reduction formula and take it in the opposite direction. or I can start with something simpler and add some stuff, is some k to both the top and bottom. And this will allow us, excuse me, this will allow us to force a common denominator. So the way to go about this is essentially multiply these denominators together. Well, it does get a little more complicated than that in a real problem, which I'll show you in a bit. But that's the idea we're going to implement here. I want this common denominator of b times d. So I have to throw in a times d to both the denominator and the numerator to keep things equal. And likewise, the whole point of doing this is having the same denominator in both fractions. So I'm going to multiply a b, and I'm writing it on the left just to make it look nicer and make them look the same. And let me just highlight these real quick. These new things I threw in, I did the opposite of the reduction formula, or really just using that same formula, but going backwards. All right, anyway, now these have the same denominator, which means that I can actually add these. A times d plus b times c. So once you have the same denominator, then you just add the numerators together, combine it into one fraction over this single denominator. You know, think if you have a quarter of a pie and add on to that another quarter of a pie, then you have 1 plus 1 quarters of that pie, now 2 quarters of the pie. So that's the idea. Now I said it gets a little more complicated, and let me show you what I was talking about. So let's say we want to simplify the following. So the way that we do this is we want to force a common denominator, so have the same denominator for each fraction here, and that will allow us to add, also subtract. Subtraction is just another weird form of adding, so the same principle applies. So what I would do is look at these denominators, look for some commonalities. So whenever you see a polynomial that's ripe for factoring, do it. We're breaking it down into its component pieces. And turns out that -3 is the number for both, right? These multiply to give me a +9, and when I add them together, I get the -6. So everything else is already as factored as it can get. Well, the important thing is comparing the denominators. So notice that, hey, those look kind of similar. So we could just multiply every denominator together. That would ultimately work, but that ends up throwing in some extra stuff that we don't really need. So the way I want to go about this is get the same common denominator in as minimal a way as possible. So this already has 2 of these x minus 3 factors. And here we already have 1, so when I'm looking at this guy, I don't really need anything from this x minus 3 over here. We've already got that more than covered. So what I really need is this x. That's something new. So I'm going to throw in a times x. So I include it up here because you have to keep things equal. But the most important thing, or the reason that I did this, was to have the x down below. And I can even turn this into an x minus 3 squared, just to keep it a little simpler. So for this term, I already have an x, but I'm missing not just one x minus 3, which is also covered over here, but I'm ultimately going to need 2 because of this term. So I want to throw in an x minus 3 squared. But if I'm going to do that, then I have to do it above as well. Now, over here, I want to get that same common denominator. So I already had a single x minus 3. That means I'm going to need another one, and I'll need an x as well. So once I throw those things in, then I have the same denominator. But I throw in an x and a single x minus 3. Those were new. So let me just highlight real quick the new things I threw in. So here both of these were new. Okay, notice I got rid of the times 1 over here. That's fine. So here also it was the entire numerator. And a single x minus 3. But I left the 2 unhighlighted because there was another one that was already there. Okay, so now we have a common denominator. And I can mush those numerators all together. So 3x plus x minus 3 squared minus x times the quantity x minus 3. And now we seek to simplify the numerator. So I would probably multiply this out, but thankfully we actually don't have to, because we saw from the beginning this was actually what we started with, and we had factored it into x minus 3 squared. So this is the fully multiplied form. So don't need to reinvent the wheel here. Now be careful with this last part. I'm distributing the negative x. So that creates a minus x squared, but here we get a double negative, which makes a positive 3x. This may look like a big mess, but it comes together beautifully. Notice that these x squareds cancel. We have a plus x squared and a minus x squared. And a new color. Notice that I have 2 positive 3x's and then a minus 6x. So altogether, those x terms cancel out as well. Right, 3x plus 3x is 6x. Then we have a minus 6x. This means that all that's left in the numerator is 9. So if there were no 9, if we had 0, then the final answer would just be 0. But that's not the case. We have a 9. Now there's no more reduction that can be done there. All right, well, thank you for joining me, and I'll see you next time with section R4.